Okay, so let's move on. That's in the economical theory of demand response, or of energy markets, by the way. This is the one part of the equation. In the case of energy market, there's a theory that's used for operators who buy energy, for example. Now you also have operators who sell energy, and you have the duo of this, where you have what is called a running cost. Here, we don't take the investment cost. So that corresponds to, for example, the energy market, where you have today, in the day-ahead market, you have to decide whether tomorrow you will sell hour by hour how much quantity. So Swiss Grid runs such a market. In other countries, there's a different entity than the grid operator to run the market, but every country in Europe has one or several areas that each have a market, where in the day ahead and other steps also, every provider needs to say the quantity Q that they will run. Since it is day ahead, the investment costs are not in the equation. Once you are in this market, you've done the investment. So you have to produce, you just have to look at your curve that says, for every value of Q that I can bid, here is my cost here. This is the case of a very flexible supplier. This is the case of a non-flexible supplier here, for example. And this is an example of a flexible supplier with a maximum capacity. Here the cost becomes, if I'm a wind supplier, my running cost is zero, because I need to monitor my system. I need to be there. Whether I sell the energy tomorrow from 11 to 12 or not, that would not change anything to the cost of my operation. And so I will be able to sell whatever my forecast is saying, and I will not be able to sell more. So if you ask me to sell more, the cost for me would be infinity. And if I sell this or less, the cost for me is zero. So those are the type of costs. And this is, for example, a typical fuel-based generator where the costs are linear at the beginning, but if you increase the capacity, typically there might be more. You also have curves that are non-convex, but those are the general curves that you see in the literature. And then, very similar to what we discussed about the consumer side, the supplier, if they go to the market, they will decide to sell the quantity Q that maximizes their revenue, which is PQ, that's the money they will get at a price P, minus the cost that they have. And then, if a market works, there is a price that emerges from the market, and this price is such that all consumers maximize the utility minus P of Q. Therefore, the quantity that they take is equal to the derivative of the consumer quantity is equal to the price, because you set the derivative of that to zero if everything is smooth and etc. And similarly, on the consumer side, the price P will be the derivative of the quantity that they sell. So that gives an easy interpretation of how markets and dynamical economical systems work. What matters is not those functions that we saw before, but their derivatives. So if I have, for example, this elastic load, which is a concave function means the derivative is decreasing. That would be the derivative, which is called the demand curve. The demand curve is the derivative of the utility of the consumption. And similarly, the supply curve is the derivative of the cost function of the supplier. And very often the supplier curves are convex. That means increasing beyond some level costs more and more. Therefore, the curves, the derivative, are increasing. And of course, if there is a non-manipulated market, then the things will balance. So the price will be the same for sellers and buyers on a non-manipulated market. So this is the economical theory of demand and supply. In a set of users and consumers and producers that have such curves, the market will balance at the intersection of the supply and the demand curve. That will give the amount that is traded, and that will give also the price at which it is traded. That's a theory, that's the perfect market. In reality, of course, there are many things that are different in reality. The market might not always work, so those curves might not intersect. There might be too much demand and not enough generation, or vice versa. So there are multiple steps of that, but in each of those steps, this is typically done. So for example, most European grids have a day-ahead market where we run such a system for producers to deliver the amount they want to do. Then this market is redispatched with the so-called real-time market, which is in fact 1 hour before real-time. And in addition to that, you have a capacity market for the reserves, and you also have secondary versus tertiary reserves, where in the case of tertiary reserves, operators are paid simply for having the capacity. In the case of having for secondary reserve, operators are paid for both the capacity and their usage and how much energy they have produced. So all of this together is the global picture of the energy provision today. Perhaps let me skip this because we are short of time. If you remember the discussion in the Norway pilot that motivated the introduction of demand response was to shift the demand curve. So here is the demand curve that people have if they are not subject to demand response. Then we see that when you allow them to have to do demand response, we see that their curve takes this shape here. And by taking this shape, the intersection of the supply curve and the demand curve is moved here from this to that here. So you see that when we're on the steep part of the supply, then a small change in the demand curve, of course, can change the prices dramatically here. Which is, of course, natural. That's what we expect. If the energy system is close to its capacity in terms of production, cannot produce more, or is producing more and more only at extremely high prices, then a small reduction can have a large impact on the price everywhere. So this is one of the motivations for demand response, and this is how this is exactly quantified and manipulated. Now, if you're an industrial customer, not just you and me with your washing machine or your electric car, but you have a whole site that's consuming a lot of energy, then you can produce your supply curves by really, then it makes sense because you can really monetize your cost of operation. You see, if you're running a big factory and you know that, for example, you can consume 10% less during 2 days tomorrow, you can translate this into additional operational costs that you will have. Perhaps you need to move production to other time slots, which may mean having people to work at night instead of during the day, or vice versa. So you can quantify those costs. So this has been done, and so the supply curves for industrial consumers are known. And there's another market for demand response, which is typically done with industrial customers, where they can provide exactly their supply curves, and then if they participate in flexibility programs, they can receive money for them. We have seen, in fact, this morning, the effect of price here, right? We see here this high price has led to the fact that the temperature drops here. I'm not showing the power consumption, but we see the power consumption is 0 here. So we see that during those two high prices period here, at least not during this one, but during at least those high prices period, we have reduced the consumption. So this is also another effect, which is perhaps more difficult to quantify with such a supply curve. But, and this is where the traditional theory of economic demand response is a bit fragile, there is something else that happens. This user, if I am this user, I'm not reacting instantly. I'm not saying, okay, here is the price, therefore I take this amount because here's my utility. No, this is not what this system is doing. The system is doing something else. Here you see that before the high price, the heating system has been heating the house, has been consuming a lot. This is called the pre-bound effect. So the manipulation of prices do not lead entirely to this equilibrium of quantity that is consumed, but it has effect before and after the price is hit. So there's a paper that discusses this, for example, the criticism of those limitations of the economic theory of demand response with utility demand and supply curves is that the user reaction is not limited in duration. And second, that end users, but not industrial consumers that are able to quantify their supply curves and their demand curves, but individual users tend to react very differently. For example, that has been seen in the US in many demand response measurements that were done. When the price is high, people switch off the air conditioning for some time, which is exactly what you see here. Here, you see optimal response to a price increase over a 95-minute period. You see that when the price goes up here, then ideally we should see this. But in reality, so that's the demand response event here. What we see is that first everybody switches off everything that can be switched off, and then that was one of your questions a few minutes ago. Of course, you don't want to be outside of your comfort zone. So if the temperature of the house becomes too low, you will heat up again. So you will start consuming again. Perhaps you will set the thermostat to a different set point, but you will consume. And when the demand response event is finished, you will have a surge of consumption here. You will consume more because you were below your comfort zone, a bit below the comfort zone here. And similarly, we have the pre-bound effect. Let's see that if users know that there will be a demand response event, they will tend to anticipate, which is the optimal thing that we've seen that the MPC should do. So loads are shifted in duration, so the things are more complex and require more sophisticated operations. In the worst case, demand response can have some weird side effects. For example, TICO makes money of its demand response program by selling essentially a secondary reserve service to Swissgrid. But in order to offer a secondary reserve service to Swissgrid, you must offer a capacity that's always available. Now, because there is uncertainty on whether TICO is able to provide, TICO, remember, is a demand response operator that reduces shuts down your heat pump when it would like to reduce the consumption of Switzerland. But if your heat pump is not working, for example, because the temperature is extraordinarily warm, we're in February, but it's plus 15 degrees, then perhaps your heat pump does not work a lot because your house receives a lot of sunshine and is perhaps already at its desired temperature, or a bit of heating is sufficient. So TICO may not have the capacity at all times to satisfy the regulation requests. So in order to do that, they need typically to match the demand response resources with generators. In the case of TICO, it's hydro. In the case of other demand response operators, it is a diesel generation. So this is limitations of this. Last, back to the question, is there a positive effect, or is it simply shifting, or is it a negative effect? So the question is loss of load. So loss of load is the amount of load. Load means, in electricity term, means the consumption. If I do a demand response event, so here I'm showing in gray the load, the natural load, the consumption of a given region of Switzerland. Now, if we do a demand response program, this is what we will have. We will have a reduction of shaving the peak. That was the goal. After the demand response event, the load will stay at a high effect, and perhaps there is a rebound at this later stage here. So the question is the integral of the load, the total consumption, when there is demand response, the pink area here, how does it compare to the gray area, the consumption I would have if there would be no demand response event? The loss of load is the difference in relative terms here. So if demand response is a pure demand shifting, the loss of load is zero. If we save energy, like Voltalis says, then the loss of load should be positive. What do we expect in general? Perhaps you are confronted with this problem. Assume you belong to the happy few who have a chalet. then you have the question, what should I do in the winter? Nobody is in the chalet in the week. I come in the weekend. What should I do during the week? Right? Should I heat it up so that when I come on Friday night, it's warm? Or should I let the temperature drop? Of course, I will let it drop below the freezing point to avoid freezing of the tubes. What is better? Of course, the story is if I let the temperature go down, when I return to the chalet, I need way more heating. So am I losing or what's better? What do you do with your chalet? I close the poll in a few seconds. And the majority of you will use policy A. You think there must be a reduction in total energy consumed, therefore you will switch off your heating and perhaps switch it on a few hours before you come in so that you have a nice temperature. Which is, well, we'll see what is what. Right? Well, first, loss of load is not the same as the rebound effect. We know that when we do a demand response event, there will be more load before or after. So that's not the question we're asking here. Here, the question is, does it compensate? I will consume more energy before or after, but if I do it after, by letting the temperature drop here, will the integral compensate? That's the question that we have here. Right. So that's the first thing to realize. Well, the answer is very easy if we remember the heat house model, and if this heat house model is true, because the heat house model is saying that all the energy that I am putting into my system goes either out and is leaked or goes into the inertia. And this is exactly the same equation as what we would call a leaky bucket. I can put heat, imagine heat is an amount of fluid, and the temperature is the height, how high the water is in the bucket. And there is a leak here. The leak corresponds to this term here. So that you will have exactly the same equation here, where C would be the surface and T the height of the bucket. Now, if I integrate this from 0 to T, I will have the following equation. And now let me compare two scenarios. If I do not interrupt the heating, so I let it warm all the time, then I have a scenario like this one, right? I'm making sure my chalet gets warm all the time, so I put heat all the time into it. If I don't, if I let the temperature drop, I stop heating when I'm away, the temperature drops, and when I come back, I heat, of course, much more, assuming I have a very powerful heat pump, and the temperature will quickly raise here. But now if you do the maths of this, you will easily see that all the heat that you've gone here, if you compare starting point and end point, where is the heat? Where is the fluid? The fluid is either in the bucket or has gone through the leaks here. But since the level of the bucket is the same before and after, the integral of the fluid is, the level is the same. So the difference in those two cases is simply the difference is how much has leaked. Now, do we leak more when the level is high, or is the leak constant? Then the leak, we know, is proportional to the temperature difference. So when the chalet is cold, it leaks less than when it is warm. So here we leak more. So the integral of the leak here is larger than the integral of the leak. And since the starting and end points are the same, the only difference is the integral of the leak. Therefore, it is true that here there is less heat that is put into my system. I use less energy. So it costs more to keep the chalet warm without interruption than to pay for the high amount of heat that I will need to bring it up to the temperature. Of course, this is a very simplified analysis, so it might not always be true what is written as in form of conclusion here. In particular, if the system is nonlinear, it might be that the coefficient epsilon of efficiency of the heat pump is not constant, but depends on the time of the day. For example, the heat pump is less efficient if it's an air heat pump and the outside temperature is very cold, so it's less efficient at night. So if you heat at night, you have a lesser coefficient of efficiency, so that may be a bit different. So it might not be a good idea to let it cool down during the day and heat it up at night because you arrive in the following morning, for example. We have seen that already with David's house. We've seen that the optimal thing for the case like this would be to heat it up even before, to take advantage of, here it's not the low price, but the higher efficiency of the heat pump. Similarly, there might be price differences. Perhaps it's the electricity is cheap during the middle of the week because nobody's there in the Alps and there's no congestion in the lines, if the problem is congestion in the lines. So there might be other reasons that change the optimum. But in terms of integral of heat, the answer is that one. So Voltalis that I mentioned is a demand response operator that has been scrutinized by the agency, the French agency that monitors and does recommendations about energy efficiency, called ADEME. So they've monitored this claim that Voltalis says, we don't give you any money, but your electricity bill will reduce. And Voltalis found that it's true for heating, about 10%, but there is no significant saving on hot water boilers. Those are the statistical findings from this report that I give here. How do you interpret this in the light of the theory that we have seen now? I close the poll in a few seconds. Closing. And the majority says B, which I guess is the true answer. I say I guess because it's plausible, but perhaps we should do experiments to verify this. And it doesn't come from other buggy reasons. But it's plausible because boilers are typically very well insulated. I mean, a boiler is a closed volume that is made to keep hot water inside, so it's easy to insulate. And because boilers were made to be used offline, to be used at times of low consumptions, traditionally there has been a market of making extremely well insulated boilers. So the boiler leakage is very small. If the boiler leakage is very small, then deferring the heating has a negligible impact, which is a reasonable interpretation. In contrast, house leakage, unless you have a very modern house that was built on purpose to be extremely well insulated, that means a Minergie P house with airflow, forced airflows, etc. If you don't have such a house, which is not the case, of course, for the houses that are controlled by Voltalis, then the house leakage is not large. Hopefully, you have an insulated house, but even an insulated house, if it's not a special energy house, has a significant leakage. So if you reduce the temperature, the leakage of the house reduces a bit. And if you do that 1 hour every day or half an hour every day of the year, then at the end of the year, you will see a small reduction. And here they find it's about 10%. Voila, that's the conclusion for this part. I would just like to mention that today, of course, those systems have been deployed to the existing large consumers, which are heating systems. Tomorrow, we start seeing them deployed for controlling electric cars and other names, where we have dynamic charging stations instead of demand response. But we have the same thing here. Now, we have similar things that if you charge at high intensity a car, then you have more losses than if you charge at low intensity. So performing very aggressive demand response might have also a negative effect on the total energy being consumed. So something to watch. But we expect here the effect to be much less than, so the effect might be in the other direction than for thermal systems. Voila, so that's the conclusion. I give a few hints on where to read if you're interested in that topic. Demand response, or in general, dynamic management of the user side of your electric car, of your heating system, perhaps also of your solar panels, is a fantastic topic that will give a lot of opportunities, and we'll see a lot of deployments in the very short future. Demand response can act on practically every time scale, but of course, it has benefits and drawbacks. The benefit is that it's extremely cheap, and we see that TECO can deploy the equivalent of a few megawatts of secondary reserve without, apart from the fact that they must have a hydro part to be able to satisfy their contract. But when they provide their energy, in fact, they simply provide a manipulation of the load curve. So by using intelligence rather than energy, we can save reserves at least. It comes as a competition to true storage. So some people call demand response a form of virtual storage, because we store heat in the houses, or we store cold into if we are air conditioning or freezing. So it's a form of virtual electricity storage. But of course, we have true electricity storage, batteries, which you know how to control through the labs that you are doing. So all those things will be deployed together in a complex system that will be the smart grid of the future. Well, that's the end of the lecture and the last lecture of the course. I hope you enjoyed it. Thank you for all your questions, your fantastic presence in this course in the difficult conditions that we have this semester. We continue to be present with you until the end of this lab. A bit later will come the exams. The last 2 years exam are already online on Moodle. So when you're done with the lab and you're up to date with all your quizzes, a good idea is to do the mock-up exam of the previous years. And of course, we will be available to all questions you may have. Take care, stay safe, and enjoy the rest. Bye-bye now.
Thank you very much. Bye.
Bye, thank you.
Thank you.
Goodbye.
Bye bye. Thank you a lot.
Bye-bye.